From now onwards we will focus on lectures, and today I will start group actions. And what are group actions, and why should we study group actions, and why we need. Today we will define the notion of group action, and this is the first lecture on group action. And the basic requirements for group actions are: you must know about the basic group theories, whatever in the undergraduate level group theories. And I'm assuming this much you guys already know, right? So let me start group actions. Okay, so now we'll learn it in a different way, right? So what are group actions? So you must have a group. For group action you must have a group, and you must have a non-empty set. Okay, you must have a group and you must have a non-empty set, and we'll say G will act on this set, right? So you have a group, right? So let my handwriting is, I guess, not so good, and because of I am writing in a writing pad, it's actually uh, actually it's not a correct way, but okay, no problem. So you have to adjust. Okay, so let G be a group. So we have a group G be a group, and you have a set S be a non-empty set. Okay, this has to be reminded. You have to remind in you have to keep in your mind that this S should be a non-empty set, otherwise you cannot define, because you will see non-empty set. Okay, so you have a group G and you have a set S which is non-empty, and we say G acts on S if there exists a function f from G cross S to S, right? Not only a function, if function has a has a property, is a special property. Okay, what are the properties of this function? So we say G acts on S if there exists a function G f G cross S to S, and we do have a property. And what is this function? Actually this is a Cartesian product of G and S. Okay, G S might be G. Okay, there is no problem, and S we have taken just as a set, right? It S may be a group itself also, right? So we don't bother about that. Okay, so we say G acts on S if there exists a function. What are the elements of this Cartesian product look like actually? So this element is actually some G comma S, right? It goes to an element of S, and we will define it as GS or G dot S or G star S, and we will define G dot S, GS, G star S accordingly. Okay, you will see, no problem, you will see, don't worry about that. So there exists a function GS. Okay, it should satisfy some properties of group act. Sub properties. The first property is, whenever you have an if you have a group, then you have an identity element, right? This group, and E dot S, this should go to S for every element, small s inside the S, right? This is the first property that should satisfy that E dot S is goes to H, or you can see E star S, there is no harm. Okay, so E dot S, if you operate E with any element of S, it should give you an element of S, right? This is the first property. And the second property is associativity, right? What kind of associativity? You could take G1 G2, two element of G, and operate with S. S means the small s, right? These all are small s. This all the small s are the element of capital S, right? So this should give you G1 G2 of S, right? For every G1 G2 inside G, and for all small s inside capital S, right? These two property, if a function satisfies, then we say G acts on S, right? These two property, just to see, you are operating G1 G2, this is G1 G2, and then operating S, it should give you the same whenever you are operate G1 G2 S, and then G1 of G2 of S, right? G1 of G2S, right? So these two property, if satisfies a a function satisfies, then we say G acts on S, right? This is the definition of group action. There is nothing more, okay? So when we say G acts on S, if there exists a function f G cross S is a Cartesian product of G and S and to S, okay? It input is an element G comma S, and output should give you the element of S, right? And it should satisfy these two properties, and then we say G acts on S, right? Okay, let's see some examples of group actions, right? So example, it will be clear whenever you will see the examples of group actions, right? So first example I should take that okay, so what kind of examples we can take? Okay, yeah, we can take, you already know the group Sn, right? That is why I told that you have to be clear with the basic notions of group theory. What is Sn? Sn is actually set of all functions such that if n to n bijections, right? This is a group, right? Where n means 1 to up to n, right? This set is called Sn, and this forms a group under the composition of mapping, right? Sn with respect to this, right? This is a group, and you take Sn as a group, and you take the set S as 1 2 3 up to n, right? So you take G as Sn, right? And you take S to be this finite set 1 to up to n. Does there exist a function which satisfies this property from G cross S to S, and such that the E dot S is goes to an element goes to S for every element S inside the S, and G1 G2 inside Sn, and operated with S is same as G1 of G2 of S? Does there exist a function? Okay, so let us define a function if Sn, sorry, not Sn, you correct, yeah, Sn is actually G, so you can take G cross S to S. How will I define this function? You take any element sigma, and I means I is an element of this set, okay? Whenever I am writing the pair, it should be understood that I am writing this element as element of S, and this element is an element of the sigma is an element of Sn, and I is an element of S. That is what, and I am defining this to be sigma of I. Sigma is a permutation, right? Sigma is an element of Sn, so sigma of any element should go to some ij, right? Of course it should go to j, because this is a bijection, and you know this what are the elements of Sn, right? Looks like this is identity sum, and some 1 2 3 1 3 2, this kind of things, okay? So this kind of things in Sn. So I will simply defining, how I am defining sigma dot I is goes to sigma of I, right? Sigma comma I is going to sigma of I. This is clear. It will be definitely a member of, this will be definitely a member of S, because sigma of any element of I, it should go to some j, right? And j is also an element of S, right? So this map is an well defined map. This f is an well defined map. So this map is well defined. Now we just have to check whether these two properties G either satisfies or not. If satisfies, then we say G acts on, thus means Sn acts on S, Okay, otherwise we will say that it's not acting on x, right? So let's set the properties. Okay, is it clear? Then this f is an well defined map, right? So okay, the first property, what it says, that e comma I, where it will go, e of I. What is e of I? E of I is actually I na. Identity means what? 1 goes to 1, 2 goes to 2, 3 goes to 3. For any I goes to I, of course. So e of s is goes to s. E of an element of small s is goes to small s, which is element of s, right? So first property is satisfied, right? E dot s is goes to e dot I. E dot I is I. Why e dot is I? Because it is an identity element of Sn, and identity fixes every element, right? It fixes every element, because 1 goes to 1, 2 goes to 2, 3 goes to 3, whatever element you take, it should go to this I. So first property satisfying, right? Second property, okay. Okay, so sigma 1 sigma 2, I am taking this sigma 1 sigma 2 is an element of Sn, right? Sigma 1 sigma 2 operated at I, which is actually nothing but sigma 1 of sigma 2 of I, right? Sigma 1 of sigma 2 of I. So this property is also satisfying. This is an element of sigma. This you can write that sigma 1 sigma 2 I, of course. So this property is also satisfying, right? So G acts on S. Sigma 1 sigma 2 of I. Okay, two member I have taken, just two member I have taken, I have from S, and this I'm trying to satisfying this property, right? This property I'm trying to satisfy. G1 G2 of S, an element of S, and it goes to sigma 1 of sigma 2 of S. Of course this is a function. Okay, so we can definitely write like this, and which is also like that sigma 1 sigma 2 of I. Okay, so this two property is satisfying, so we can say G acts on S, right? So where G is Sn and S is the set containing 1 to up to n, right? So example 1 has been done, and we only lefting out, no sorry. So let's move to example 2. Okay, you can take an equilateral triangle. I know this is not look like equilateral, but you have to adjust. This is the vertex A, this is B, and this is C, right? This is an assume that equilateral, I know bilateral triangle. This is an equilateral triangle, right? So these are the vertices, right? You take S as the vertices of this equilateral triangle. What are the vertices? A, B, C, right? This is the vertices of the triangle. And G, you can take the G as, okay, so this is a group, right? And of course you know it as a D3 group, but yeah, you can, this is identity R1 R2, where R1 is rotation by rotation by 120 degree, R2 is rotation by 240 degree, right? R1 R2, and this is a group, of course this is a group, right? No, not this is not group D3, right? So this is actually cyclic group. Okay, this is actually isomorphic to three, it contains 3 element, and this is actually isomorphic to Z3 or something, you know. So Z R1 R2, and R1 is a rotation by 120 degree, and R2 is a rotation by 240 degree, right? And I am taking this as G, and the vertices of this triangle ABC as S. Just think about it. Just how can G acts on S? Will will G will acts on S. So if acts, then how, what kind of mapping or function you can give me? So first you have to check this, that if you have a function that if G crosses to S, is this map, how you will define that, such that the map is going to well defined. G is an element of identity, and if you take any element of identity and any element of A, which is equal, you should give us the element A, right? Identity is rotation by 360 degree, right? Identity, what is identity? Identity is actually rotation by 360 degree, right? Rotation by 360 degree, right? So if you an element, if you rotate it element by 360 degree, it will remain same, don't you think? If you are rotating it by 360 degree, it will remain same. The A vertices, you just rotate it by 360 degree, right? It will remain A. You rotate and clockwise or anti-clockwise, it does not matter, you just rotate it by 360 degree, it will remain same, right? So this identity of A, same identity E of B will give you the B, and E of C will give you C, right? Whatever take, right? Now you can check that R1 of A, R1 means rotation by 120 degree, right? So R1 of A, if you rotate it by anti-clockwise direction, right, 120 degree, now you are 120 degree, it will give you the B, and R1 of B will give you C, and R1 of C will give you A, right? Similarly for R2 you can definitely write, and the first property is it is satisfied, not first property, I am checking the well definedness of this group, that you are taking an element of G cross S, that means this means this is an element of G and this is an element of S, and it is a element of S, of course, checking the whether it is this map is well defined or not, how I can make this map well defined. Same for R2 of A, R2 of B, R2 of C. R2 is a rotation by what, 240 degree, you just rotate it by 240 degree, right? So this will go to C, right? And this will go to A, and this will go to B, of course, right? A will go to C, B will go to A, and C will go to B. Okay, this map is a well defined map, right? So first condition is already satisfied, because you are taking E dot A is goes to A, but identity fixes every element, right? So if of any element of A, it goes to A. If E comma A goes to A for every element A inside the element, the set S, right? So now you are lefting out with only property, first property, this property is first property is satisfying, right? And we are only lefting out with second property, that means you are taking R1, R2 and some A consider. So this should give us R1 of R2 of A. Let's see whether, so R1 R2 of A for any two element, okay? So R1 R2, okay, we are multiplying R1, and R1 R2 means you are taking R1 and R2, R1 is a rotation by 120 degree, and R2 is a rotation by 240 degree, right? So so 120 and 240, this will go with the 360, and 360 of A is actually R1 R2 is actually, because R1 R2, it will give us the identity, of course, right? R1 R2, this is an element of order actually 2, this is an element of order 2, and this is an element of order 3, and this is an element of order 3. So it will give us identity R1 or 2, it will identity, and it should be operated with A, right? This is already give you A, because this property, this, right? R1 is a rotation by 120 and R2 is a rotation by 240, the R1 R2. r1 r2 is an rotation by 360 degree, right? Rotation by 360 degree. So it will go to A. And what is r1 of r2 of A, which is r1 of, what is r2 of A? R2 of A is actually C. And r1 of C, what is r1 of C? This I'm using this, and this is actually, so second property is already satisfied. Okay, so you take r1 r2 or r2 r3, so any element you can take from G. Okay, and this will definitely satisfy this property, right? So r1 r2 of A, it will go to identity of A, this is A, and r1 of r2 of A, it will give us r1 of C, which is r1 of C is actually A. So second property is also satisfied, right? So we can say G acts on, sorry, G, not G, you can take this, yeah, G acts on S, right? Okay, so for example 2 has been done. Now we can define something, sorry, example 3. What kind of examples we can take? Okay, let's take another example. G to B, you take GL in R. G, actually this, yeah, GL in R. This is actually set of all invertible n cross n invertible matrices with elements are from real numbers, right? This all you know, right? So G is actually GL in R, which is the set of all invertible n cross n invertible matrices, which elements are from R. That means real number, right? So, and you take S to be Rn, the column vectors, right? This is to be Rn, this set Rn. This S to be, you can take this S to be and Rn. How will you define this group action? G acts on Rn. How G acts on Rn? So if you have any element A inside element of G, and if you have any element V is a column vector inside Rn, this should, A dot V goes to simple AB, right? That means you have function from G cross S to S, right? So I am defining this to be A dot B. A is an element of GL in R, and V is an element of Rn. This is a column vector, right? You can take any matrix, n cross n matrix, and you can take any column vector. This should go to, and it will of course it will give you an column vector, right? Of course it will give us a column vector, right? So we can definitely take, right? This is, of course it will go as this, and this is an element of Rn. This map is an well defined map, right? Now you just have to check the first property, that is E means identity element, identity, and V, this is actually V, right? There is nothing to check. The first property is already satisfied, and you have to take A1 A2 and any element V, it goes to, or matrix multiplication, you can definitely A1 of A2 of V, you can definitely take. This is actually this the second property has also been done, right? So this G, you can try this kind of properties, this just two properties you can try yourself, right? So I'm not going to show you explicitly, so I might go very first, but these are very trivial things. You definitely have to do in yourself, right? So A1 A2 of V, this is, yeah, this example. So but now can we take S to be G also? Don't you think that S is a set? We can definitely take S to be a group also, right? We can definitely take. Don't you think? Yeah, of course we can take. So yeah, let's see this kind of example. One example for this will two examples. G to be G and S to be also G. Okay, so we need to find a function from G cross S to, sorry, G cross S means G cross G to G. We have many functions. Cartesian product. You have learned homomorphisms like that. So they have defined this kind of things. Okay, Cartesian product group actually, right? This is a product group, and this is a, we can definitely find a function. How will I define this function, right? This is the actual. Okay, so you take any element G, any element S. S is also an element of G, right? It may be same. These two may be same, may be different. We don't bother. It goes to G dot S. GS, right? So this is actually called left multiplication by G. Or multiplication by G. Okay. So first property E dot S is goes to ES. ES is actually because ES and S is an element of G, so it will, of course it will be S, right? So we don't bother, right? So first property is done, and the second property, what is the second property? G1 G2 of S. This S is also an element of G. Keep in your mind, okay? Don't forget, otherwise you will not be able to apply this kind of properties, right? This group has this since S is also this group, and that is why we do have some special properties, right? That is why we are allowed to apply. Otherwise it might we cannot apply, right? So oh my god, what happened? Yeah, so G1 of G2 of S. Okay, so of course group is the definition of group. Okay, G1 of G2 group properties of group. What is the properties of group? Is it should satisfy the element associativity, right? This is I am using the associativity. This is also also right, satisfying, right? So this group acting on itself, so we call G acts on itself by left multiplying of G, but this is called G acts on itself by left multiplication. This is called actually left multiplication. We can also define for right multiplication. This is actually same. You can try yourself. Left multiplication. This is actually called left multiplication. We will define another kind of action. This is also G acts on itself by conjugation, right? Last example, right? I'm giving the last example. I will not give any examples. So I think that these 5 examples are more than sufficient to learn to understood what actually group actions are and how does it actually acts. Okay, 5. This is called 5. Okay, so I am defining G cross. Sorry, I don't know why I am writing this. So G cross G to G, how I am defining any element G and any element S. Reminder that G is also an element of G, S is also an element of G, the same group G, right? So this goes to GS G inverse. This is called action by conjugation, right? Or conjugacy, right? So action by conjugation, right? Do you know this map is a well-defined map? This question I am leaving to you, that do you know this map is a well-defined map? This is a conjugation relation, and this relation is an equivalence relation. Do you know? So this is a very interesting action, right? Further we will study about this action, right? And this action is called action by conjugation. and you take any element G and any element S of G, two elements S of G, and you are operating as like GS G inverse. This is also an element of G. Do you know? Because this is an element of, this is an element of G, this is an element of G, this is an also an G as an element of G, S is an element of G, and G is and G group should be closed under the operation. So this entire guy is an element of, this entire guy is an element of G, right? So this map is an well defined map. Now we are lefting out with whether this acts on G. This is a group action. The question is, the straightforward question is, does G is a group, this is an action? You can check, definitely check the first property. First property is very obvious, E dot S. What is E dot S? E dot is actually ES, E inverse, E is actually S. First property satisfied, there is nothing. You just have to check the second property, right? What is the second property? It says you take G1 and G2 and S, operate S, it should give us G1 of G2 of state. Yes, okay, so we can definitely take, right? So what is this? By according to this, G1 G2, sorry, this is actually G2, this is actually G1 G2 is in G1 G2 inverse, right? I'm just defining as whatever, how actually defined, right? Actually defined. Okay, so you can take G1 G2 S, and A B, the whole inverse is actually, if you B inverse the inverse, so you can take the G2 inverse, G1 inverse, you can definitely take. So you can take G1 of G2 is G2 inverse, this separately, and G1 inverse. So what is this? What is this? Is not, it is G1 of, actually yeah, actually this also actually G2S, actually it called G2S, but you can take G2 dot S actually, because G2 of S is actually defined as like that, right? G2 of S is actually defined like that, okay. And G1 inverse, and this is an entire, and you can definitely take G1 of G2S, G2 dot S, right? The actual motive is here. This is also, you have to take this to be this, right? And G2 of S, you can and by definition this is, you take this an element of another element, and G1 of G2 of S, okay. So second property is also satisfying, right? So this group, this is an action, and this action is called by action by conjugation, right? So I think this was for today. Yeah, or I should define something, orbit. Yeah, I should define orbit, right? So okay, so we are defining another notion today, what is called an orbit, right? So groups, and okay, so what we have studied till now, just recall what we have studied. We have a group and we have a set S, right? We say G acts on S by this property, and this hey, you see this kind of thing, right? I think you guys are all already okay. So okay, now I'm defining another notion of group theory, which is called an orbit. Okay, the first question that immediately should come, what is by listening the word orbit, what is the orbit? Orbit is actually, yeah, orbit orbit is actually this kind of things, right? This is called an orbit or something. So we have studied electrons, protons, yeah, something like in physics and chemistry, right? They have orbits, right? The orbits actually like this kind of things, okay. We'll see. So okay, what do we mean by orbit? Okay, let's not define the orbit, right? Okay, now define something G is a group. Okay, I'm not writing G is a group, right? You should be understood. I'm writing that G acts on S, right? And it should be understood that G is a group and S is an empty set. Okay, so that means G acts on S means G cross S to S is a function. There is a function G cross S which satisfies the above two properties of this above what I have defined in earlier, right? Just earlier. So G cross S to S, right? And let S be an element of S, right? So we say orbit of S. Orbit of S. Sorry, the small orbit should be an element of S. Right? Orbit is a small element of orbit of S means the orbit is actually fine. Orbit actually is for an element, right? This is not a set or not a group element. No, sorry, not for group. This is a member of a set and S. This is a member of S, and orbit is always is of some element. Okay, of course, orbit of S is defined by, this is actually called ORB, orbit of S, right? Element of S. Okay, this set is actually defined by GS, where is G inside G will run the entire G, right? And S in element I am taking, suppose, okay, I will give you example, don't worry about that. This is called an orbit of S. Do you know this orbit of S is an okay, what is this? G dot is an element of S, right? This is an element of S, right? Of course, because G dot S should be an element of S, na? Because G cross G dot S goes to GS, and this is an element of, because the function is G cross S to S, right? So this is an element of S. Do you know? Can you see that orbit of S is a subset of S? Okay, it should be clear to you. I am taking all the possible element G dot S, and where G travels, sorry, where G varies, right? And S is fixed. For fixed S, I am defining the orbit, right? So orbit of S, you can see that orbit of S you can say should be thought of as the set where S travels under the action of G. Under the action of G, where S travels, okay, S, but this, by this action S is traveling somewhere, right? Because orbit of S is containing this kind of elements where G dot S and G varies, okay, where it should be thought of as the set where S travels under the action of G, okay, under the action of G, okay, under the action of G where S travels, okay, this is called the orbit actually, where S travels under this action of G, okay. So examples, you can take the previous examples whatever we have defined, okay. Sn acts on S, where S is 1 to up to n, right? And for G is an Sn, and S is sorry, it's not, this should be capital S. S is actually 1 to up to n. I have just shown that this group G acts on S by the action defined earlier, that you can take any sigma inside S and any I inside S. Sigma y is goes to sigma dot I is goes to sigma y. Of course, this is an element of S. This map is an well defined map, right? So if I say that what is the element of orbit, orbit is an element of this, orbit is always be of an element, right? So if I take orbit, orbit of 1, what can you say about the orbit of 1, right? So by definition, what is this? G dot 1, where G is inside Sn, right? Okay, so G dot 1 is goes to G of 1, right? Rather you can take this to be sigma s, right? This then it will be clear to you, right? It will be definitely sigma dot 1, where sigma inside Sn, right? So don't you think this actually, see, this actually sigma of 1, sigma inside Sn, don't you think the orbit of 1 is actually 1 to the every element, it will 1 to up to n, every element it will. So if you have identity element will give you sigma 1 will 1, and if you have 1 2 element, it will give you the sigma of 1, sigma have 1 2 inside Sn, it will give us 1 2 2, it will give you 2. And if we have 1, you of course have 1 2 element inside this group, 1 2, this will give sigma as an element of as sigma as 3. No, sorry, I'm committing a mistake, right, yeah, sigma of 1, it, don't you think it will be 1 to up to n. You have an element identity will give you sigma of 1, which is 1. Okay, you have an element one 2, it will give you sigma of 2 is actually, sorry, sigma of 1 is actually 2. You, yeah, actually I was correct, 1 3. You have an element, these all are element of Sn, right? Every element is kind of element of Sn. So this will give us sigma of 3, sigma 1 is equals to 3, right? So every, you take any element inside here, right? If you have any I inside here, so you will take 1 comma I, and sigma of I, sigma of 1 will go to I. So every element will cover, okay, every element will cover. I am just taking a simple example, right? Simple example for S3 group, right? And then it will be more clear, right? Why Sn, the orbit of any element of 1 or any element, it will give us the entire set. Why? Okay, so not only for 1, it will be orbit of any I, right? It will be an orbit of any I, and I is an element of S, right? So, right, so I'm taking a simple example, group S3. What are the element of sigmas of S3? Actually identity 1 2 1 3 1 2 sorry 1 3 2 3 2 3 1 2 3 1 3 2. And what is my S? 1 2 3. If I can say what is orbit of 2, which is actually sigma dot 2, which is actually sigma 2, so as sigma inside is 3, right? So sigma of 2, why sigma varies? Sigma can vary, sigma can be this, 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 sigma. If sigma is identity, what will you give? 2 goes to 2, of course it will give you 2, right? Sigma of identity fixes every element. If sigma is this, the first element, identity, right, this, and it will give you 2. If sigma is this 2, but sigma should vary, right? Sigma varies over S3. If sigma is this, sigma of 2 is 1, right? This, if sigma is this third one, 1 3, it will give us 2, and 2 is already we are included in the set. Yeah, we can take 2. So if you take this 2 3 as a sigma, it will give you 3, right? So, and if you take this 2 goes to 3 is already included. If you go 2, this is 1, right? So you cannot, you are not, you can take 1 2 3, they are repeating elements, so you don't have to take the repeated element in the set, right? So you can say that orbit of any element, orbit of 2, which is equals to orbit of 3, which is equals to orbit of 1. You can verify it, of course. It is not an it is not so hard task. Okay, you can definitely verify in yourself, right? So okay, so let's take an example. Last example I am taking, that for orbit where G may not be a same, the entire set, the orbit of any element is not necessarily be the entire set is. I am taking this kind of examples right now. So what kind of example I should take? That okay, so this is orbit where the orbit of any elements will not be the entire set, yes, right? Okay, let's take the conjugation action. G cross G to G, and any G and any S is goes to GS G inverse, right? This action I am taking. So what is the orbit of E? The first element orbit of E, which is actually orbit of E is actually G dot E, right? Where G inside G, and identity will give us the entire G, right? It is very clear because this is already G inside G, because identity will give us the only G element G, right? So there is nothing to show. And orbit of E, right? And what is the orbit of any element S, which is GS G inverse, right? And G inside G. If G is abelian, if G is abelian, this G S G inverse, you can take G inverse of S. This is actually ES, which is actually S. Okay, this is just for commutative or abelian. Okay, if G is abelian, then orbit of S. If G is abelian, then orbit of any element S is actually the singleton set S. We take any element here, any element here, it will give us the orbit of S is only singleton element. Okay, so this is an example where orbit may not be the same entire set, right? And you can definitely take some other examples also. You can definitely make. I just have to remember what kind of examples you can take, that G may not be the entire orbit of any element is may not be the entire set, right? So yeah, so you can verify this, and this much, I think this much for today is enough, and we'll make more precise examples and the notions of group theorem, stabilizers, and we'll define an equivalence relation to show the orbit is actually anything but the equivalence classes. Okay, so blah blah. So this kind of things we will define, and I think this much for today. And so orbit of any element, if G is abelian, so G is abelian, then orbit of, do you know why orbit of any element? Of course is because G will commute into G, and we are only lefting out with S, right? So there is nothing to vary G, because G and G inverse will give us the identity, and identity of S is of course X. And why this is E, you know, which is actually, you can take, what is this actually, D dot E is actually nothing but G G inverse, and E G inverse is actually G inverse, which is actually E. orbit of any element of E, right? G E G inverse. Wait. G E G inverse. So it will only give us the identity, right? Sorry. Yeah, I made a mistake, right? Okay. Yeah. That's why it seems. Yeah. Actually, I made a mistake. Yeah. So what is the by definition? G E G inverse, where G inside G, which is actually nothing but the identity element. Sorry. Orbit of any element of E is actually G dot E, which is actually G E G inverse, which is actually identity. This is nothing, because this and this will give you G inverse, and G inverse will operate with G will give us the identity, right? So this will give us the only single element identity. Any element of identity will goes to identity, and orbit of any element of S is goes to if G is abelian, it goes to singleton S, right? And what example I have earlier defined. What is the element orbit of E? No, sorry, orbit of 1. Yeah. So this mass is for today, right? We will meet for in lecture 2, right, where we'll define the stabilizers and some more precise things about group actions, right? So I think this much is for today. Yeah, thanks for watching, and bye.